All right, our next topic is confidence intervals for the mean, population mean mu, and this is if sigma is unknown. So we have a new formula to use. We have the following: x bar plus or minus t subscript alpha divided by 2 times s divided by the square root of n. So this is the formula we're going to be using. Now, here's our setup. Here's our example. Suppose we're given a sample of size n equals, let's say n is equal to 14 from a normally distributed population. So we have a population that is known to be normally distributed. Now, we know that if the population is known to be normally distributed, then we have met the requirement for the central limit theorem to apply. And so our sample size of n equals 14 is sufficiently large. If the population is known to be normal, then any sample size meets the sufficiently large requirement. If this piece of information were not given or were not known, then the sample size would need to be, yes, it would need to be 30 or more. But in this case, 14 is sufficient. Let's suppose we have also computed, suppose we have been given that the sample mean is known to be 61.1. Let's suppose the sample standard deviation is given to be, let's say 14.2. All right? And suppose we want to construct a 90% confidence interval. All right? Well, in part because of space restrictions and in part because this is the way it's commonly done, I will from here on out essentially always, I will typically abbreviate confidence interval CI. That's pretty standard. So we need to construct a 90% confidence interval given this information. All right? Now, anytime this formula is given, right beside it is always written the following: d period f period equals n minus 1. df stands for degrees of freedom. Specifically, what a degree of freedom is, why it is even important, how it enters into this, is not something for this course to consider. It's a topic we discuss in graduate school. It has to do with the technical details of what's happening here. For our purposes, all we need to know is this: anytime you're using the T table, anytime you're using the T table in our course, anytime you see a formula involving T, you will see beside it a computation formula for degrees of freedom. Depending upon the formula you're working with, the computation for degrees of freedom might change. In this particular case, for this particular problem type, anytime you use this formula, the degrees of freedom are n minus 1. That's all we need to know from your side of the camera. All you need to know is that the degrees of freedom here are n minus 1. So for our purposes, if n is equal to 14, in our case, we know, so this is not given, this is computed. The sample size is given to be 14, so our degrees of freedom are given to be, or not given, are computed to be 13. So when we use our table, as we discussed in the previous video, when we use our table, we're going to be in the 13 degrees of freedom row. The next piece is, all right, what column do we need to be in? Well, if we're doing a 90% confidence interval, remember our value for alpha is, if this is a 90% confidence interval, alpha is 0.10. If we have 90% confident, then roughly speaking, we have 10% or 0.10 error. And because we're working in a symmetric distribution, we take half of this alpha in each of these tails. Now, the table only asks for the value in the right side, the right tail, but because the right and left tail are equal due to symmetry, it doesn't matter which one you pick, and tables typically will take the right tail for other considerations that are beyond the scope of our course. So, what we need to do is take alpha, divide it in half, so our alpha divide by 2, and that's why this is given alpha divide by 2 to remind you, find alpha, and then divide it in half. In this case, this is 0.05. So this number is not given, this number is not given. These numbers you will compute. You compute those values, and then those are used in this computation. All right? I'm going to erase this to find some space. Once we have 13 degrees of freedom, alpha over 2 is 0.05, the rest of this falls into place because to compute our formula, it is now essentially plug and chug. That number goes in here. That number is given. That number is given. The only thing we need to find is our value for T alpha over 2, and that comes from the table, which we talked about in the previous video. So the rest of this is straightforward. X bar is given to be 61.1 plus or minus. Don't know yet. We'll look that up here in just a moment. But these numbers are known. This is times. S is given to be 14.2. Divide by the square root of, in this case, 14. And we need to find our value from the T table. Again, previously we've discussed this. This should be straightforward. We're going to be in the 0.05 column. I have my table here. You will take yours. 0.05 column. We are in the 13 degrees of freedom row. And so the value I have from my column, from my table, is 1.771. You should be able to find the table value from these two pieces of information. The table value is 1.771. That is T alpha over 2. That is this number. 13 degrees of freedom row, 0.05 amount of alpha in one tail. And so find where those intersect. I have 1.771. That goes here. And everything else is calculated. In fact, this is finished. 61.1 plus or minus. Find that number. And I believe I can handle that. My machine says 1.771 times 14.2 divided by the square root of 14. And I have 6.721. 6.721. And that is our 90% confidence interval for the population mean. What this means is if we did, taking samples of size 14, if we did a large number of confidence interval computations, then approximately 90% would be covering, we say covering this population mean mu. We're trying to estimate the population mean. We know it falls somewhere. We don't know where. We have computed this confidence interval, and this is extremely approximate. Some people don't agree with this interpretation, but this might or might not contain this population mean mu that we don't know. But the likelihood is 90% that we have captured this, or that this is covering this population mean mu. So X bar is given, S is given, N is given. From N, compute degrees of freedom. Alpha, the confidence level must be given. Alpha so compute alpha, divide by 2. So find the values in this column, this row. That gives you the T value. Everything else is plug and chug and compute. So what I'll do next in the next video is just do several examples of this to get you the feel for how this works. This should be pretty straightforward.